actually called isotopes of the element carbon. Okay, so the mass number here, 6 plus 6, 12. Mass number here, 6 plus 7, 13. Mass number here, 6 plus 8, 14. So those are different isotopic forms of the same element. So then what we do to talk about those different types of carbon is say what it is, carbon, and then we say the atomic mass number or mass number. Carbon 12, carbon 13, carbon 14. Have you ever heard of carbon 14 dating? Carbon 14 dating? Well, it basically, carbon 14 dating can be used for things that were alive. So once something's alive, basically it interacts with the atmosphere and it incorporates some of its atoms are going to be, carbon 14 is pretty rare, okay? But if you're living like we are, we've got some of our atoms in our body are carbon 14.
Why is it so rare?
Because it has what we call a half-life. It basically decays into other things. And why is it unstable like that? It just has to do with the ratio of having those extra neutrons in there. Yeah, so it wants to fall apart and I think form nitrogen or something. But when we die, heaven forbid, or when a plant dies or when an animal dies, it no longer is incorporating new carbon 14, so the clock starts ticking. The carbon 14 is kind of unstable, so it just starts to decay. And scientists really understand the rate at which that decay occurs. So they can just kind of put the clock backwards and understand how long ago that object was living. So that's carbon 14 dating, okay? Yeah, I know. Another isotope that's in the news is U-235, uranium-235. It's one isotopic form, one type of uranium that can be used, I'm thinking of 235, 238, can be used for atomic bombs. I can't remember which one it is. Okay? But again, it's the whole isotope thing. Yeah. So to say which isotope of carbon, all we got to do is say the atomic mass number. Then this one actually doesn't have to do with isotopes, but this is actually looking at 3 different elements: the element hydrogen, the element helium, and the element carbon. Okay, the symbol is H, He, and C respectively for those elements. A lot of times they'll put the symbol for the element in the upper left-hand corner. They'll put the atomic mass number. So that's what that is. If you're a visual person, I kind of like how your author's done this. For instance, well, maybe not. Yeah. Here with hydrogen, okay, this particular form of hydrogen has just it has an atomic number of 1, means it has 1 proton. And here, look, the mass number is also 1. So it doesn't have any neutrons. It's just a proton. Okay, it has 1 electron around it. This is the helium that we drew the other a little bit ago, and this is actually a look at remember this is the nucleus of a carbon-12 atom. It's got 6 protons and 6 neutrons. All right. Oops. So one of the things that I'm just fascinated by is that we're here at all, that the matter that makes us, let alone the matter that makes us conscious beings, has assembled itself in the way it is. And I just think that's so cool. So basically, as you probably already know, atoms join together to make compounds. Okay? Like water is a compound. H2O, 2 H's and 1 oxygen. Okay? Carbon dioxide is a compound. Table salt. The formula for table salt, as some of you know, is NaCl. Table salt's a compound. Okay, the last one up there, C6H6, probably the most common one of that is benzene. Okay, those are all compounds where atoms, like this slide says, atoms have stuck together. They form a chemical bond. The reason that chemical bond forms has to do with electrons, basically, either being shared or transferred. in the science of studying the universe, one of the things that scientists look for is carbon monoxide. What's the formula for carbon monoxide? CO. Good, carbon monoxide. The fact that they can find carbon monoxide molecules in outer space just totally amazes me. Actually, when they find carbon monoxide just around the bend, probably is maybe a star-forming region. Okay. We'll get there. We'll get that here. Okay. So, we talked about light. Remember, we can look at this poster. Okay, light is actually, you can say light is all of these energies if you want to. Like light is gamma rays and light is radio waves. Light is electromagnetic radiation. How that light interacts with atoms, okay, is very important. Okay, to trying to figure things out. Trying to, right? We can say you have 4 possibilities when energy, this is my energy, interacts with matter. So energy interacts with, my finger is an atom. Energy interacts with matter. 4 things that energy can just pass on through. Okay, oh wait. An emission can occur. That energy can be absorbed by the matter. That energy can be transmitted by the matter. Or that energy can be reflected or scattered. So here are some examples. So, for instance, a light bulb is an example of matter that emits light or energy. If you, not the new light bulbs, but the old-timey light bulbs, like your grandkids aren't going to know this, but they're kind of warm, aren't they? When you put your hands around them, they're not very efficient. It's not all light. Some of that's that infrared radiation. Okay, so a light bulb doesn't just emit visible light. Okay. An example of energy being absorbed is if you weren't thinking and it's a sunny hot day out, or maybe it's a cool hot sunny day out, but anyway, if you're wearing something black, it will absorb the sun's energy. Okay, that's an example. And just because of the color, we'll talk more about colors. Why black is, and if you want to stay cool, you wear a white shirt, right? Okay, black absorbs energy. That's an example of absorption. An example of transmission is a window pane. Glass on a window pane. Basically, it's awesome because sunlight comes through. But like, for instance, if you've ever, on a sunny day, gotten into your car to start it and the windows have been rolled up, okay, what happens is light has come through your window, interacted with your interior of your car, turned into heat, and that that heat doesn't get back through. The heat is stuck in your car. So that's visible light going through a window. And then the other thing is reflection or scattering. So reflection or scattering is the reason we don't bump into things. Light reflecting or scattering off an object so you don't bump into it. Okay. If we were to stay here till midnight and like shut all the windows and make it really dark in here, you could not see anything. You would bump into things because there's no light to hit the object and come back to you. Okay, so let's go back to kind of the white shirt, black shirt sort of thing. So this white for this poster right here, okay, white we said if you wear a white shirt, sun's out, you're going to stay nice and cool. The thing, and that's the way I always remember, I go back to what color shirt you wear if it's a sunny day and you want to stay cool. White. Why? Because all of the colors hit you, okay, and they all bounce back. And it's so amazing to me. Basically, all the colors, that Roy G. Biv we talked about, the red, orange, yellow, green, blue, indigo, violet, all of them scatter back at you. Because when you turn on the light and get white light, it's all colors of the rainbow. Okay? But it's all like mixed together. I just think that is so cool. Okay. We have sunlight landing on several objects here. It's a busy figure. So if you see a white object, that means nothing is absorbed, okay? If you see a red object, that means red is absorbed and everything else is scattered back, okay? This down here says,
Would that be reflected?
oh, yep, thank you. Thanks. That's what the slide says. Red is reflected, thank you. Red is reflected, everything else is absorbed. So if red is, so white light hits it, okay, ooh, but try a different color. White light hits it, okay, and red is, scatters red light, thanks. It scatters red light, and that means everything else is absorbed. So that's OI, G, BIV is absorbed. So if you're a visual person, that's kind of what it is. Pick on the tree over there. So the color that gets scattered back is the color that we see it is. So green is scattered. Green is scattered. So that means that what is absorbed is ROY BIV is absorbed. Okay. So there you go. Okay. So we talked about the overall structure of an atom, the little nucleus that has two parts, the protons and the neutrons. We count them to get our atomic mass number. And the electrons out there, actually, if the electrons equal protons, we have a neutral atom. But the other thing about electrons, and electrons help make our compounds. Another thing about electrons is they actually exist at what we call energy levels. So even though they don't, it seems like they, like if this is an electron orbiting the nucleus, okay, and it doesn't really orbit like this, it's actually in a cloud. But kind of where its location is part of kind of how much energy it has. So electrons are at energy levels, okay, and the thing about energy levels is it can be here at this level, or it can be at a higher energy level, or electrons can be at a higher energy level. And usually as it gets a higher energy level, literally it's farther from the nucleus. It's like, okay, lots of energy, okay? But it can only, it's like skipping steps. It can't be, it's not like a continuous. It can't just kind of decide where it wants to be. It's here, or here, or here, okay? It's discrete energy levels. And that's important. As it takes these steps from a low energy level to a high energy level, that's important. The whole stepping up sort of thing, or stepping down. So if you look at just a normal atom, normal neutral atom, and you look at the electrons around that atom, it wants to actually have all those electrons with the lowest energy possible. They're all going to be kind of crowding in on the nucleus, even though there's a lot of space. Electrons occupy a lot of space. That's what we call the ground state. Okay, they're all just couch potatoes by default. That's lowest allowed energy level. But, and I have an example coming up here in a minute, in this tube, it's neon. They aren't marked. I think this might be neon. In this tube, this old-fashioned tiny tube, is neon gas, okay? And when I plug this in, I'm going to plug it in just for kicks. When I plug it in, it sends electricity through that gas, and the electrons around those atoms go, whoa, okay? They transition up, okay? And when they transition up, okay, they get a bunch of energy, but then they say, I'll go back to couch potato. And then they transition back down again. When they transition back down again, they give us light. That's it. That's the way it works. And so there'll always be this characteristic color because kind of that jump will give us a color. That jump gives us a color. It worked before. Oh, don't read it. You saw it. Did you see it buzz earlier? we say that the electrons around those atoms are being excited by electricity. Electrons are being excited by electricity. When they fall back down, they give us that light. That's the way fireworks work that way, that same way. You know, when we see the beautiful fireworks, there's a delay, and I don't know quite how that works. But basically, they excite electrons around atoms, and it gives us these different colors. So I think that was so cool. Let's turn that off for now. We're going to come back to that in a minute. Okay, so this whole jump thing, did you kind of catch how in this example we had electricity? It absorbed electricity to go up, okay? And as it fell back down, it emitted energy. So it absorbed electrical energy to go up. It emitted light energy going down, okay? So we kind of had this absorption and actually emission started going on. Okay, so this whole, I'm kind of getting back to the sun's fingerprint that we looked at kind of as a slide opener, the whole spectrum of the sun with those dark lines. That's exactly what's happening here. We call those absorption lines. So it's important that we kind of get this idea of this sort of specific jump. Actually, I have a figure coming up to kind of show you that. So, let's see. You know how you take a prism and you take sunlight, you pass it through a prism and you get a rainbow on the other side? Okay? Take sunlight, pass it through a prism and you get the Roy G. Biv, all the colors of the rainbow. That's actually what we call a continuous spectra. Okay? That's exact. If you want to put rainbow next to that, you can. Okay? Basically, you've taken white light and divided it into its colors. And I'm going to compare that then to two other types of spectra. Continuous spectra, no lines. And what are these lines? Here we go. Emission line spectra. Now, if you think about emission, hopefully you can take the word emit out of emission, emit. And those must be where the electrons are emitting light. And I'm hoping you think, when you think emit light, you think of it going just like this, going down. It emits light when it goes from a high energy to a low energy. It emits light. That's exactly it. So just like the gas that's in here has a specific color, that is just because the element's going to have that signature color because it has this jump it's able to do after electricity promotes those electrons. It falls back a certain amount of. Okay, so emission line spectra, we'll see an example of those. It's going to be what we call bright line spectra. Absorption, hopefully absorption line spectra, you think of the word absorbs, okay, and absorbs means takes in. So absorption line spectra are kind of, this isn't a very good example, but the absorption part was where it took electricity, right, to go ahead and that electrical energy to bump back up. Okay, if we could see that electrical energy it took, it would create what we call an absorption line spectra. The first one, the emission line spectra, actually, I've heard it called a bright line spectra. And just like the description shows, you'll have bright colored lines. An absorption line spectra, I've heard it called a dark line spectra. And I'll show you what those look like. Okay, so we have continuous spectrum, emission spectrum, and absorption spectrum. Continuous spectrum looks like this. So we have a source, okay, and actually where that light bulb is, we're going to switch out and we're going to make that a star at some point. Okay, but for now it's a light bulb. So the light bulb gives us white light, okay. We go ahead and take a small piece of it, use a slit to get a small piece of it, send it through a prism, okay, and that prism will make it split out into its Roy G. Biv. So can you see the Roy G. Biv kind of going backwards? Red, orange, yellow, green, blue, indigo, violet. So continuous spectrum, no lines. All right. Here is an emission line spectrum. So the emission line spectrum, notice you don't have the bright light anymore. What you have emitting or glowing is a cloud of gas. Your cloud of gas is emitting or glowing. They call it a, let's put it this way. Oops. Sorry, my builds aren't doing right. What's missing here, I didn't mean to take it away. This is a prism. You can see it on yours, but it didn't show up here. So basically, you have this cloud of gas that is glowing. The cloud of gas is glowing. Why is it glowing? Well, it had some sort of source. This says it's a hot, rarefied gas. What was its source? Heat. It wasn't electricity, but heat basically promoted those electrons up. They're falling back down, and we're privy to the glow. Okay, so it's glowing.
Okay, when we say falling back down, is that towards the nucleus that you mean falling back down?
Right, yes. Falling back down. The thing is, it's falling back down like, if this is high energy and this is low energy and the nucleus is here. So it's kind of both. It's like a location falling back down, and it's falling back down with regard to energy. Yeah. So it's less energy, closer to the nucleus, exactly. So the thing about the hot rarefied gas that's glowing, it will give, I know we're going to see it a particular color. It's going to be green or pink or blue. Nebula are beautiful like this. But it's actually, look over here, I know, this over here. Actually, if we were to dissect that light that's coming from that nebula, it actually is giving these discrete bands. Do you see the kind of the bands, the purple, the blue, the 2 at the green, the 2 at the yellow, and then the 4 over there at red? That is an identification as to what that substance is, what is in that, generally what elements are in that cloud. Okay, why are they there? Because electrons are falling down. But the thing about different elements is you're going to get a different set of those lines. Those are called spectral lines. And can you see what we call a bright line spectrum? Bright line, because that's what it's going to look like. Okay. And then the yang to that yin are absorption line spectra. So notice what's the difference here. Now we have our source again. We have our source behind the cloud of interest. That blue thing is, we're like, oh, what is that? Well, basically you shine a light through it, and instead of getting the whole light back, you're going to get basically some chunks of energies that have been taken out. Okay? Some chunks of energy have been taken out by that cloud. Which chunks of energy? Well, it depends upon the identity of the stuff that was in that cloud. Okay, whatever's in that cloud is going to give you a set of energies that's going to be absorbed. Okay, so absorption line spectra look like this, where basically instead of getting the entire light bulb, entire energy, you get it, but you have chunks taken out. So I didn't memorize it, but you can flip back and forth. Can you see where these dark lines, the kind of 2, 1, 2, 2, and 4, these dark absorption lines are basically the reverse image of the bright emission lines on the previous slide. They go together. They're the same substance. Okay. I like, if you're a data sort of person, this is kind of neat. Okay. Of course, you recognize the rainbow with the chunks taken out of it, kind of the Roy G. Biv going backwards. But down here, it's kind of a nice XY curve, where along the x-axis we have wavelength, where this is the shortest wavelength, short wavelength, and this is the long wavelength, long lambda. And then here is intensity. So basically you have dips where those dark lines are. I think that's kind of cool. They're both saying the same thing. So those lines, the locations of energies where energy, the locations, the wavelengths where energy was sucked. is an indication of what's in that cloud. All right. Is this way? Yeah. Okay. So I've talked a lot about kind of like if this is the nucleus, and so kind of like I kind of say electron energy levels, going up. So that's exactly what this is. Kind of showing you energy level 1 is the lowest energy level, and up to 5, okay? You can kind of see they get closer together. This would be showing you emitting energy. Does that make sense? Because we have down arrows. Okay, these would be emitting energy. And the step that the electrons fall between energy levels, that's how much energy is going to be emitted. So I like this because can you see where, the shorter the wavelength, like this is a short wavelength, like NM stands for nanometers. Okay, if you're like me, you're like, I don't necessarily know what a nanometer is, but I do know what a nanometer is. N is a metric prefix for nano. It means 1 millionth, 1 billionth, 1 billionth of the base unit. But notice over here we have shorter. These are relatively short wavelengths, and remember with short wavelengths there are more energy. And doesn't it look like they're more energy? Look at that big step. It's the size of the step that gives you the energy. Okay? These little steps, a long wavelength means low energy. So that's all possibilities of the single electron around a hydrogen atom. Hydrogen just has 1 proton in its center. So if it's neutral and lucky in outer space, it'll have 1 electron. Those are the possibilities for it. It's thinking. How are we doing? What's that? No, you're good, you're good. Good, thanks. Okay, again with the hydrogen. All right. So here is actually an emission line, a bright line spectra emission line for hydrogen. I think this textbook doesn't emphasize Kirchhoff's 3 laws, but Kirchhoff's 3 laws, his first law is continuous spectrum. The second law is emission spectra, and his Kirchhoff's third law is absorption spectra. But do you see where actually these, the different colors, okay, the color purple, for instance, is about 410 nanometers. That's the wavelength. The color red is a longer wavelength. It's actually in nanometers, 656 nanometers. So that's kind of where those are. And actually these transitions, these middle transitions, those correspond to those observed lines of hydrogen. Okay, so the 410 through 656, this one right here, that's all visible. But these energies actually are in ultraviolet, and those energies are in infrared. So I added you're not seeing things, let's take this away. So there's some more spectral lines of hydrogen, but instead of being bright lines, they're dark lines. They are absorption lines. They're that third type of spectra, okay? But they're at the same locations. So what I did was to bring the bright line spectra from the previous one and put it underneath this dark line spectra. So The top one there is absorption, and the bottom one there is emission. Same element though, so the lines are in the same spot. Okay. So helium, so we talked about hydrogen. After hydrogen we have helium. So we have 1 proton in hydrogen, 2 protons in helium. Sodium has many more than that. Neon, many more than that. But these are like the fingerprints of those elements. There's hydrogen again. So there's back to the sun's solar spectrum.
Sorry, thanks, Susan.
All right, so we're going to take a break in a minute.